Thank you, Jean. And of course, you forgot to mention that one of the topic actually of the science of science is that is to understand, what is the secret of success. And I want to say that a key part of the success is to have excellent advisors, right? So you forgot to mention that part. But so let me put this one up, and it's a real pleasure to be here, and indeed to talk a little bit about the line of work that is happening in my lab on what we increasingly call the science of science. And I put up a question for all of us saying, what should be the short way of saying, is it sci-sci or SOS? I tend to think sci-sci is cooler, but SOS has other meanings that we probably don't want to invoke. But let me tell you the way we think about when it comes to science of science and why we think that we have a set of tools, let's say those of us who work in networks and self-organized systems and so on, to address that problem. And the reason why we think we have some tools that may be relevant is because when we think about what it takes to be successful and to achieve something, either in science or any areas, then there are two pieces to the puzzle, right? One of them is the performance piece, which is what you do as an individual, what papers you publish, how many of them, so where you publish, as well as your productivity and many other things that depend solely on you. Those are actually the performance elements. And then often we tend to think that success is also something that we do. But what I would like to actually argue that is that the recognition piece, which could include citations, could include awards, could include access to the right institution, access to the right people, and so on, that is actually something that, yes, it depends on the performance, but it's not solely performance. And what the argument I would like to make here is that the performance really is about us, but about you in particular. That is an individual property of a scientist, but success is really about us. That is that success, those many measures of success that we have in science are really collective properties that we as a community confer to the paper, to the scientist, to the institution, to the journal, and so on. And if you accept the fact that the success measures, including SSA citations and many other things, are collective ones, then suddenly all of us who work on networks and in big data are in business, because that's where we built our career, is to try to understand big data sets and patterns within the big data sets. So that would be really the line of thinking that I will pursue here, is that it's very difficult for us to measure performance outside of sports, right? In the sense that, of course, when it comes to a runner, we know exactly there's only one performance measure, how fast you run. In science, however, it's very difficult to say who wrote really objectively the best paper, who is really kind of the better scientist. Most of those things actually are coming from the community's perception that are really in the second rubric, which is our recognition or success measures. So our journey has kind of included several steps in this. The first one, actually many years ago, was spearheaded by then a new student in my lab, Dashun Wang, where we started to ask, could we really understand what determines the long-term impact of a paper? What are the parameters that determine that? And of course, one thing that we always often believe is that where you publish matters a lot, right? But on the other hand, that's not always the case. And we captured where you publish based on the impact factor of the journal where we go, and the impact factor change very widely. These are some of the journals that I regularly publish in, and you see that there are very big differences in the impact factor. But we know, all of us in this room, that how misleading this is, because if you actually take papers published within the same journal, the number of citations that paper gets, for example, 10 years later, change very widely. This is a distribution of the citations 10 years after the publication in 3 journals, Cell, PNAS, and Physical Review B. Very different impact factors. And you see that really the difference is not so high. They're only kind of different in the fact that the higher impact journals get a few more very high impact papers. But to be honest, whether you publish in Nature or Science or any other high impact journal, most likely our papers in those journals will get very few citations, despite the fact that they're in a very, very high impact journal. So So journal itself is doesn't predict the future impact. The citation count doesn't either, in a sense that if you take all the papers that, let's say, 5 years later got exactly 50 citations in the same journal, and you look at it, what happens after that, you see there's a huge differences in their future trajectory, even though you pinned how many citations they got 5 years later. So it shows again how unpredictable the story is. And we know the citation counts have lots of problems, and that we don't have to go too deeply into that. Now, to show the real chaos in this problem, here I'm showing you a bunch of papers using the same data set that Kathy Berner actually showed earlier, which is the physical review data set. And what you see is that several papers and their citation patterns in time. So each line corresponds to a different paper, and you see that some of them, of course, have a high impact. They jump up and then slowly die out. Others hardly take off ever, and yet others kind of wake up later in their career after publication and start acquiring citations and die out again. So the challenge was, given the randomness, almost chaotic, and I'm using the word chaotic more like a synonym, not as a scientific term here, nature of these patterns, is there a way to really model this? And that was really the surprise of this particular project, is that we realized that at the end, there are only 3 patterns that matter when it comes to the long-term citation patterns of a paper, and even the short one, right? One of them, of course, is the intrinsic value. And this is the toughest part, right? This is the one that we say it's so difficult to measure. What is the intrinsic value of the paper? But the other one is preferential attachment. That is, the more citations the paper got, the more visible it is, the more likely I will encounter it by reading other papers, and therefore that I will have a chance to cite it again. And of course, here's the bad news. Every paper has an aging component. That is, no matter how big the discovery you make, after a while it becomes common knowledge, and our colleagues don't feel the need to cite it again. We kind of know about that, right? And that's kind of and when we looked at the data, it turns out that actually aging follows a relatively simple log normal pattern. And when you put these pieces together, you can write up an equation that tells you what's the chance that your paper will get another citation next year. And you can even solve that in a relatively close form. And let me show you what this formula tells us. Well, it tells us that there are really 3 parameters in the story. One of them has to do with, and this is kind of a typical citation curve that this particular formula predicts. And the first parameter is the fitness, which relates to the intrinsic value of the paper, and that really controls how high will the paper shoot. The second one is really the peak, where it reaches the peak. And here is the bad news, that most papers reach their peak within the first 2 years of their publication, which is one reason why the impact factor is really measured within 2 years, because after that is really a free fall. And what I mean a free fall is that there's an exponential decay as you get away from the peak. And the third parameter just tells you the longevity, that is how fast that impact decays in time. So the beauty is that this particular formula is telling us that only these 3 parameters matter. And you see that if you change the parameters, you get very, very different looking citation curves. Some of them have shoot up early and then decay. Others shoot up later, right, and then decay. And yet others even later, and hardly register just by changing these 3 parameters. Now, fine, well, how many parameters we need to fit an elephant? I don't remember the precise number, but 3 parameters is actually a very high number of parameters. It turns out that the longevity doesn't change much from paper to paper, so that's relatively constant. And so let's see if it works, right? And here are kind of 4 papers from the physics literature that have done very differently regarding their impact, right? This guy has early jump and then decayed very fast. This one was discovered later and so on. Others, not much is happening. So question, could a formula that capture all of these diverse, very, very different type of behaviors? And the answer is yes. If you rescale these curves based on the formula, what it's telling us, they all collapse exactly on the same curve. So they are all manifestations with the different parameters of the same underlying mathematical pattern. And of course, I could have chosen these 4 papers to fit my data, but in reality, when you look at all the journals, Nature, Science, Physical Review, and so on, all the papers that are there are actually very well fit with the data. So this is what we call data collapse, very common actually in statistical physics, where you, instead of fitting the curve, what you do is that you rescale the curve based on what the formula is suggesting you in these parameters. And then if they all collapse onto the same curve, then it means that your formula is more or less right. And that's what we see across many, many journals. So what is this telling me? What it's telling me is that there is really a universal pattern in the way we actually cite things. And the reason why it exists is because citation is a collective process, right? We all contribute a little bit to that. And when we add all of those things together, we get a very reproducible pattern. And one of the most exciting predictions that comes out of that is that the total impact of the paper, which is the total number of citations that the paper will ever get over its lifetime, doesn't depend on all these three parameters, but depends on only one. All the other parameters fall out, and only in this fitness parameter that kind of stays into the problem, which was very remarkable for me. So at the end, it doesn't matter when your paper reaches your peak, nor does it matter how fast is the decay. One parameter, which is kind of related to this fitness of the paper or the originality, is purely determining how many citations will it ever get, which is the area of this particular curve. So which was very unexpected to us, but it kind of again shows the power of this collective nature of how we cite papers. So of course, a paper is a product, right? It's a paper of the product of ideas and the way we kind of convert the community. But when you look at science, really, we also have another unit that is just as important as the papers themselves, which are the scientists, which are the producers of the ideas. So the question is, how do we think about the scientists and their impact on the community in the light of the products they have, which are the papers themselves? And so kind of illustrated, let me show you my own story, right? So this, what you see here is all the papers that I have written up to a few years ago, and the 10-year citations of them, that is how many citations they got within 10 years after their publication. And when you look at my career, you see, so each dot is a paper, obviously, and you see that I have three very distinct phases. So first of all, for the first 10 years, I was very, very busy. I wrote lots of papers, but I wasn't getting anywhere, right? So that's kind of my first decade of my career, very obvious, right? And then when you look at, then something happens right after 10 years, network come along, and suddenly I'm kind of publishing one high-impact paper after the other one. So once again, I want to emphasize, those high-impact papers are not because of me, but because of you, because you cited it. I didn't cite those papers, right? And so when it comes to that phase, it's really cool, right? Everything seems to be working, right? But the real question, of course, that my dean wants to know is that what happens after that, right? And when you look at the data, it's a little bit ambiguous. So the gray, because we haven't had 10 years past to really measure the numbers, the gray are the one that we actually predicted based on the formula that we had earlier of how many citations we'll get. And the red, up to that point, there wasn't enough data to predict. So, but the real question that everybody would like to know, including myself, is that is it worthwhile to continue? Am I in this particular stage that not much is going to happen, right? So that's a question we really wanted to ask. How does the career of a scientist unfold? When do we make our highest impact work? And are there predictable patterns within a particular scientific career? And in order to do that, we're going to focus on one particular measure. We're going to first look at when do you make your highest impact discovery. And the way we do that is to say, well, we're going to just find all the close careers in science, and there are quite a number of them. And then we say, when did he or she publish her or his most cited paper, right? So in this particular case, I hope my career is not yet closed, but nevertheless, when you look at it, it was 13 years after my academic life, that is since my first publication, that I published my highest impact work. Now, interestingly, this is a review article, so this is a review of modern physics. Everybody would count this paper to be more relevant, but nevertheless, the method is not perfect, but it gives an idea of what happens, right? So now we took all the different scientists and we asked, where do people make their highest impact work, right? And we did so starting from a hypothesis that is very ingrained in science, particularly in physics, but is generally ingrained in most creative areas, that creativity rests with the young people, right? So there's lots of evidence on that, or lots of anecdotal evidence of that. Einstein himself once claimed that if a physicist doesn't make his or her big discovery before 30, then he's a dead wood after that. Wigner even wrote a limerick on that, to kind of a little poem to describe the same phenomena. And this is just not only anecdotal. People who focus on the genius literature, they have provided lots of evidence that the vast majority of discoveries, particularly in science, happen early in the scientist's career, typically kind of like in mid to late 30s, maybe early 40s. And while there's a shift lately, actually, towards later careers, as Benjamin Jones has shown from Northwestern, that is still true that most creative work happens to be relatively early in the career, which is really bad news for people like me. Right? So then the question is, what happens when we look at all the careers, not only the geniuses, right? The problem with these studies is that they all focus on geniuses, and we would like to see what happens to us, right? And the way we did it is that we put all the careers together, and we asked, where does a scientist have his or her highest impact discovery? And that would be actually the red dot. You see, so these are the careers of individuals. And we did the statistics of that, like this, how many years after, what's the probability that after 10 years you begin your career, you publish your highest impact work, and this is the distribution that we found. Again, the probability that your highest impact work comes 10, 20 years, or 30 years after within your academic age. And when you look at it, it's really discouraging, particularly for people like me, because it says that I'm about 30 years into my career, so I am actually a dead wood according to this, because the chance of me making another major discovery is really, really small. Most people make their biggest discoveries, or the highest impact work, is within the 20 years of the career, and then there's a free fall after that. So, okay, so based on this one, I should start kind of, an alternative career. But then we started looking deeper into the data, and we randomized the data. What does it mean to randomize the data? We took the same career for every scientist, but we changed the papers randomly, the impact of the papers randomly. And to our surprise, in the randomized careers, we got exactly the same curve. Now let's wrap our mind around this. What this means actually, in very short, given that I have only 10 minutes left, is that really it is not about when you make your biggest discovery. It's not about the age or the stage of your career, but about productivity. Because the randomized curve is nothing but your productivity curve. So what this suggested to us is that really, each of your papers has exactly the same chance of being your biggest impact paper, but because your productivity drops kind of 20 years out of your career, or at least on average it does, therefore the chance of making the highest discovery is relatively low. And indeed, when we actually take, when we line people's career up from the first to the last paper rather than in time, this is what you see, a bunch of scientists who's from the first to the last paper, and then we put an orange dot whenever his or her highest impact paper is, and we do a tally of that, it's completely uniform. So in other terms, the probability of success or the highest impact paper is completely uniform in the space of the projects. What is not, but because the productivity is much higher early in the career and there is a drop down there, then therefore, you know, it also the chances of having your highest impact paper drops. One way to think about it is that science is a little bit like a lottery. We're picking papers randomly from a certain distribution, and because we pick most of our lottery tickets in the first 20 years of our career, most likely where our winning will actually be there, right? And much less likely to be later when we kind of stop buying lottery tickets. So now the question is, so this is actually the good news for me and for some of us in this room, that as long as we keep doing it, right, the impact could actually come. There is no age limit really in science. And let me put it this way, you know, if you look at Frank Wilczek, it was his very first paper that landed him the Nobel Prize. And when you look at John Bland, a chemistry Nobel Prize winner, it was actually a paper that he wrote after he was kind of forcefully retired by Yale. And then he went to another university to continue his work, and that's when he made this discovery that 50 years later got him the Chemistry Nobel Prize. So the innovation is not age dependent. The trying is age dependent. The attempts to make innovation what seems to be age dependent. So then how do we scientists work? And one way to think about it is that we're kind of a random product or impact generators that you know, we pick projects. So we pick projects from a random pool with a certain probability P, right? So that's kind of a random number that we pick, and then we bring some knowledge onto it. That is that to take that idea and turn it into a higher or a lower impact paper. So we're going to call this one the Q factor or the quality factor and things like that. So the idea is that I work as a scientist, that I pull a number from a random number generator, multiply it with my Q factor that is unique to me, and I get a certain impact out of that. Now, of course, the question is, how does this Q factor depend on your productivity, on your age, and on the probability from which you are pulling things? Because there should be dependencies, right? You would think that if you are an experienced scientist, that you have a high number of papers, you know you pick better ideas, right? You know how to select ideas, as well as you may be able to have a higher Q factor because you know how to bring those ideas out. At least that was our expectation. So then we did the statistics to see how do these parameters depend to each other. And to our big surprise, the random number, that ideas that we pick and the Q factor were not at all dependent on each other, and neither the random numbers or the total number of papers. So experience or this quality factor don't depend actually on the random numbers. So which really means that these two numbers actually completely, we have a separate distribution that all of us picks the ideas from the same pool, independent of you know, how experienced scientists you are. But then you have your own Q and N, and the Q and N have a very weak dependence on each other, but very weak, so weak that actually we can go ahead and ignore that, right, 0.09. So what we find is that the lock element decouples from N and Q, and to high degree, N and Q themselves are also decoupled. That is your Q factor that is intrinsic to you and the number of papers you publish, your experience. So if this is the truth, then we can actually find the formulas, which we did, to go ahead and measure what is the Q factor from a certain number of publications that the scientists had. And this is just to give you an idea, this is how a low Q factor scientist looks like. Here's a medium and here's a higher Q factor. So what the difference is, right, is that this person keeps putting one high impact paper after the other one out, and this person actually is putting much lower impact papers one after one because the multiplier is much lower. Now, the question is, how does Q depend on career stage and time? Because I thought that the Q factor will increase. You know, I'm much more experienced now than when I just finished graduate school, so I'm much better at turning an idea into a higher impact paper. And it turns out that I'm dead wrong, and we couldn't wrap our mind around this data, but when you actually look at it, so these are the Q factors measured in function of the time for the low Q factor scientists, and you see there's hardly any fluctuation within the career, so it's completely constant. Here is the higher, and here is an even higher Q factors. The bottom line is that we don't see the Q factor increasing or dropping in time. That is, the ability to take the idea and turn it into a high impact paper seems to be the same from the beginning to the end of the career. We don't know where this Q factor comes from. We would like to understand it. This is something that we can't really understand why is so. One of the reasons this paper has been under review for over a year is because we've been trying to actually wrap our mind around that, as well as the referees. What does this mean? But at the end, we did lots of tests. It's very stable in time, but it doesn't actually, but there's not an easy way to kind of explain where it comes from, but it seems to be there. But once you have the Q factor, we are very accurate of predicting, for example, how many citations the scientists will get throughout their career. All we need is how many papers the person published, as well as the age index and everything else. So this single parameter seems to be very predictive of the whole career of the individual. The only thing I can add as a scientist to my career is to publish more and more papers so that to bring that lock element out as much as possible. So just to kind of summarize what the Q factor really means, and I want to kind of emphasize, is that that if a scientist have a low Q factor, even if he or she picks a very high impact idea or a very good idea, it will not result in a high impact paper. But scientists who have a high Q factor, you know, if they pick a low P, they're still going to have a not high impact paper. But if the high Q factor and a high P, a high luck element and a high Q factor could result in a very high impact paper. So one way to think about it is that we need to kind of encourage people with high Q factors to be productive, to bring out actually that Q element from their career. Now, how are we doing time-wise? I think I have a few minutes only. Okay, so in that case, I'm going to do a little jump here, and normally I would tell you a little bit about how credit is assigned within a paper. That is, we have actually developed a few years ago an algorithm that allows us to look at a particular research publication with multiple authors and figure out how much credit from the community each author gets for that particular paper. And the reason why it actually works is because credit allocation is not based on what people have done on that particular paper, but it's really based on the community's impression of what that has paper, or who really contributed to the paper. And individuals, for example, who have a strong track record in the particular area, and there are co-authors on the paper, they get more kind of credit than those who don't have a track record in that particular area. One way to think about it, that if I publish with the Pope a paper on network science, that's still my paper, right? Because the Pope has no track record actually in network science. But if it's about religion, it's his paper, right? Not much I can do about that. And I would like to finish up with the project that is kind of underway, that is very appropriate to talk about here, which is kind of, we realized that the National Academy has a really cool data set about performance and success. Performance, of course, being what scientists have done, how high is the impact of their work, and success measure in this particular case, whether you get elected and how early you get elected into the National Academy. And here the question, of course, is not, we're not here to predict whether somebody will be elected to the National Academy. That's a whole different question and doesn't interest us. But the question is, how early in the career an individual gets elected, in what academic lifetime, depending on when he or she made their highest impact discovery. So the control parameter, the outcome we want to predict is that how fast after the discovery has happened. And you see there are major differences of how many years does it take actually to get elected in the academy. Some people got elected 11 years into their careers, others 47 or 48 years, and so on. And the reason why we're interested is because we have a hypothesis, because whether you get elected depends on two different things. One of them, of course, is the scientific excellence and performance, but there are also social factors, the network components, right? The proximity to people who really appreciate your work and to what degree they are part of the academy already. So to give you an idea, here's Eric Cornell, and this is when he got elected. This is his kind of, you already know what this figure is. And in addition to looking at the impact of his work, we also built up who are the collaborators within the National Academy, who are the people actually who wrote papers with him, as well as who are the people who cited his work, and so on. And because the idea being that the more closely interconnected you are with previous National Academy members based on collaborations, co-collaborators, as well as citations, the more likely that your work will be appreciated by the community. And so we actually have separated several what we call performance measures, as well as network metrics. You know, network metrics is like how embedded you are within the community. And here's the good news. At the end of the day, I'm just going to briefly say that, is that it's really the scientific excellence that matters the most. What is the highest impact paper, and as well as the cumulative number of citations, but the social component also has a strong predictive power in that particular case. This is something in the work, and this may be something that we may submit to this colloquium if the time is right for that. So I would like to kind of, since I'm running out of time, I would like to acknowledge my collaborator. This last work is the work of Jasmine, who's sitting there. And of course, none of this would have been possible between Roberta, Dashun, who were really key people in my lab who pioneered this area. And thank you very much for your attention.